welcome to this presentation on robust and scalable autonomous greenhouse control, an algorithm that we developed for the third autonomous greenhouse challenge. This competition is led by Wageningen University and research from the Netherlands and also Tencent from China. The goal for this competition is to maximize the profit by growing a lettuce in a simulated greenhouse, and the criteria is to get a higher profit, which is the price for selling the grown lettuce per unit area minus the upkeep cost per unit area. We're given the ability to control some parameters of the greenhouse, such as heating, lighting, CO2, and ventilation. And we can also observe some information such as the outdoor climate, the indoor climate, and also some stats of the plant. The challenge for this greenhouse first is that the controls need to be fully autonomous. There shouldn't be much human intervention. And the second challenge is that the limited nature of the data, that the access to the simulated server is very restricted, so every data that we get needs to be used very efficiently. And another challenge is data heterogeneity. By that, we mean that first, there's different types of controls. Some need to be predefined before planting, such as the maximum intensity of the lamps. Some can be changed daily, such as the plant density, and the other can be changed per hour, such as the temperature and CO2 set points. The same thing applies to the observations as well. The climate information are by hour, and the plant information are given by the day. So here's a quick overview of our algorithms. Coming from the different types of controls, we designed two modules to deal with controls with different properties. The first module is Bayesian Optimization, and we use this on controls that are fixed throughout the planting period, such as the material of the screens or the intensity of the lamps that I mentioned. For the rest of the controls, such as heating and CO2 set points, we have the model-based reinforcement learning module. These two modules are not independent. They form a closed learning loop, and they result feedback onto each other to get an overall better control scheme. We'll talk about the details of both of these modules, and first is Bayesian optimization. So what is BO? BO is a black box optimization technique. We can try different combination of controls and use it on the server and eventually find the best one, but trying all combinations with brute force is just not possible. What BO does is essentially a smart way to find which control to try so that we can find the best policy with as few tries as possible. And this algorithms works really well on low dimensional data. So we use this on controls that needs to be predefined before planting, such as screen material, lamp intensity, or the cap of CO2 output. Since these controls are fixed throughout the planting period, we don't need to worry about changing them according to weather or something, and thus the dimension is low and BO works wonderfully. What about the rest of the controls? This is where model-based reinforcement learning comes in. Reinforcement learning is a sequential decision-making process. What we have is an environment and an agent. At each step or at each day, the environment will tell the agent what the current state is. To put into the context of the greenhouse challenge, the state includes the climate inside the greenhouse, outside weather, or the status of the plant, etc. And the agent will then use the information to formulate an action. These actions are our control scheme, including CO2 and heating set points, or how to change the plant density. The environment will then tell the agent how much reward it will get for taking this action at this particular state. Because in RL, we want to have a reward at every step, so we calculate the one-step profit, which combines the difference in profit during one day and also the utility cost for this day. We'll then use some RL algorithms to learn a policy pie to maximize the total reward or the net profit. In this way, it will take into account of both the reward it can get for this day and also how the action will affect the future states. To improve data efficiency, we use something called model-based reinforcement learning. So initially, we just have some random policy, and we use it to access the simulator to get some data, and we use this data to train a local greenhouse model. What this model does is essentially trying to mimic the behavior of the online simulator. With the local model at hand, we can use our algorithms to optimize a control policy that works really well on our local model. However, there might be some errors in our model, and thus we need to try the newly trained policy on the simulator, get fresh data, update the model, and train the policy again and rinse and repeat. Since we learned a local model in MBRL, all data samples that we get from the server are always represented somehow inside the model, and the policy will mostly use the local instead of the online model to train. So this algorithm is very data efficient in RL literature. Additionally, To increase the speed of the learning process of the local model, we use some domain knowledge and design two modules. One to predict how will the climate inside the greenhouse will change according to outside climate and previous control parameters, and another model predicting how will other things affect the properties of the plant itself. And this is the gist of our algorithm. So here's a quick recap. We have two modules. We use Bayesian optimization on controls that need to be fixed during planting, and use model-based reinforcement learning to learn the rest of the controls that need to be changed according to weathers, etc., etc. As far as we know, this is really novel in horticulture literature. To learn a better model, we separate the features and learn a separate plant and climate model. This algorithm is entirely data-driven, and the combination of BO and model-based allow us to use data samples very efficiently. We don't require any domain knowledge, and I'll argue that the only place we use domain knowledge is the separation of features and the two climate and plant models. However, if more domain knowledge are given, such as if we know the exact cultivar of the lettuce and we know exactly, say, how the weight would change according to heat and CO2, we can substitute it into the model. This will also improve the speed of the algorithms since the search space is now smaller. It is also very adaptive to the change of settings. If we want to apply these algorithms on a different greenhouse, at a different location, or on a different type of plant, we don't need to change the architecture. We only need to gather some new data, retrain the model, and everything should still work fine. This is the end of the presentation, and thank you very much.